Right, Year 12. I'm recording this to help you out with the practical problems exercise that I set you on differentiation. I know that students can find this a bit tricky at first, so I thought I'd show you a couple of questions. The first one here is pretty much question 1, although I've changed the number from 20 to 30. And I'm going to go through this one and kind of talk to you about these questions in general with this question, and then I've got a geometry one that I'm going to go through as well. There's a lot of writing your own expressions or formulae in these questions, and then using differentiation to find maximums and minimums. But you do have to be able to write your own formulae, which students can find quite hard. Anyway, let's get straight into it. The first one says the sum of two numbers is 30. Find the maximum product of the numbers and verify that it is indeed a maximum. So these are two random numbers, so I've got to assign these a letter. Okay, I'm going to use x and y, classic. So the sum of them means to add them together, so x plus y must be equal to 30. I've basically translated the first line into maths. And then it wants the maximum product of the numbers, so I need to find maximum product, and I'm going to label P for product. So what we need to do now is write a formula for P, write a formula for the product of the two numbers. Product means multiplied together, so here's a formula that would work out the product of the two numbers. Okay, and I've got to work out the maximum value of P. Now there's a small problem here. Normally, if we wanted a maximum value of something, we'd differentiate it. Example, if you wanted to find the maximums on this cubic here that I've quickly written, you'd have to differentiate it. Okay, and then set this dy dx equal to 0. Alright, you've done this quite a lot in class. The problem here is I've got the product with two different variables in it, which is makes it very difficult or impossible at this stage to differentiate. What I've got to do is use this top statement to replace y with some function of x. Okay, so I've got to do a cheeky bit of rearranging and substitution. So if we take x plus y equals 30 and we subtract x from both sides, we suss out that y is always going to be the same as 30 minus x, and we can substitute this into p equals xy. So then we'll get p equals x multiplied by 30 minus x. Okay, I've replaced that y there with 30 minus x. Now we've only got x's in, so it's almost ready to differentiate, but you know that we can't differentiate this as it is. It needs to look like a polynomial, so we need to expand this bracket. I'm quickly going to expand this bracket, and there we are. We've got p as a function of x only. We're ready to go with the differentiation. Okay, so let's differentiate this. Remember, you're taking 1 off the power and then multiplying by the old power. So here we've got a power of 1. If we take 1 off of that, it will go to x to the power of 0, which is 1. And then we need to times 30 by that 1. So that will differentiate to 30. Here we're going to take 1 off that and it will become 1. And we multiply by the original power, which is 2. So there's our gradient function, if you like. Our rate of change of p with respect to x. Our first derivative, lots of different ways you could describe this. So if we want to find a maximum value of p, we need to set dp dx equal to 0. Just in the same way that we would have done for a maximum value of y or a minimum value of y, we differentiate and set it equal to 0. So max slash min when dp dx equals 0. So I'm putting 0 in. 0 equals 30 minus 2x. Solve it for x. X is 15. So the maximum product must happen when x is 15. Okay, let's see what that product is. If x is 15, and come back up here and suss out that actually y itself must also be 15 because x plus y equals 30. Okay, perhaps a bit of a coincidence, but there you go. So the two numbers are 15 and 15, and when you multiply those two together you get 225. I mean, if you try some other pairs of numbers up here, you'll struggle to beat 225, won't you? 10 and 20 add together to make 30. 10 times 20 is only 200. Okay, 12 and 18 add together to make 30. 12 times 18 is, ouch, whatever 144 plus 72 is, but it's not bigger than 225. I'll leave you to calculate that. Anyway, so I found what we think is the maximum value. I mean, we pretty much know it is, but the question has asked us to verify that it is indeed a maximum. So I'm going to use the second derivative of this to verify that it is a maximum. So let's work out the second derivative. The second derivative of this, 30 will disappear, and this here will differentiate to minus 2. So that tells you that it's about to go down. From the stationary point, it's about to go down, so it is a maximum. Okay, and we've got written on our note somewhere that when the second derivative is less than 0, you get a maximum. So that's finished that question. Okay, now I'm going to move on to the slightly more practical problem I wrote down earlier, to excuse all the door banging. Okay, let's read this then. The shape shown is a wire frame in the form of a large rectangle split by parallel lengths of wire into 12 smaller, equally sized rectangles. They look a bit like squares in my diagram, but you know, they might be rectangles. Given that the total length of wire used is 1,512 millimeters, show that the area of the whole shape A is given by this sort of nasty looking expression here. It is just a quadratic. The fraction makes it look a bit grim, but it's just a quadratic. Nothing to worry about. So we need to form an expression for the area of the shape. Excuse me. Well, this whole shape is, one big rectangle. Okay, and along here we've got 6 small squares, so we've got 6 x's going along here, and up here we've got 2y. So in fact I'm going to write next to my sketch 2y there and 6x there. So I can already see one way of writing down the area of that whole rectangle. Okay, we can write down A equals 6x multiplied by 2y. Alright, which is A equals 12xy. Oh, that's lovely, but we've got x and y in there, just as we had in the previous question. So we've got to find some other expression with y in it so that we can substitute in and just get the area in terms of x, which will hopefully look like this. So there's some information we haven't used in the question, and that's this 1,512. The total length of all of the wire used is 1,512. So what we're going to do is get an expression for the total length of wire used. Okay, let's think about horizontal wires and vertical wires. We've got 6 x's along there, we've got another 6 x's along the middle there, and we've got another 6 x's along there. So the horizontal wire is 18x. So I'm going to write wire. We've got 18x on the horizontal, and then on the verticals we've got 2y, 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 2y. That's 12y, isn't it? 1, 2, 3, 4, 5, 6. No, it's 14. So that's 14 y's going vertically. Okay, and that's the length of the wire, but I'm told in the question that the length of the wire is 1,512. So I don't need to write W equals, I can write 1512 equals. Okay, now then, all of these numbers are divisible by 2. So we need to divide them all by 2. Okay, you can hear my calculator tapping away. So, whoops, I've divided it all by 2, and I'm going to box that off. Okay, and I'm going to box this off because these are the two things I'm about to use. What I'm going to do is rearrange this for y and then throw it in there. What's slightly annoying is I've got a 7 here. If I had a 6 here, it would make things fairly, well, much easier because 7 and, 6 and 12 would have a common factor. So this is going to be a bit grim, but this is what leads to that over 7 there. So, you know, I'm confident we're going in the right direction because when I rearrange this, I'm going to have a divide by 7, and you can see a divide by 7 there. So let's rearrange this for y. 756 minus 9x equals 7y. Okay. 756 minus 9x over 7 equals y. Alright, and then I'm going to substitute that in up here so that I'll get an expression for a only in terms of x. It's not going to look very nice, first of all, but we know that. So that's what it looks like, and hopefully if we multiply that out, we're going to get that one there at the top of the screen. I can see 12 nines, 108. I'm not going to do 12 times 756 divided by 7 in my head. Although 756 divided by 7 I can see is 108. Anyway, let's not worry about the simple mental arithmetic. If you get your calculators out, you will soon work out that it does give you the correct expression. There it is. Okay, so we've got, let's just put the question back up here. We've managed to do the first bit, which is probably the hardest bit of the question, to be honest, that's got us down to this formula. Hence, find the maximum area enclosed in this way for part B. So, max when dA dx equals 0. Okay, so I need to differentiate my area function here and set it equal to 0. Let's differentiate it. When you differentiate 1296x, you'll just get 1296. This, sometimes people can get a bit confused by this. You want to see it as 108 over 7 multiplied by x squared. Kind of ignore the fact that this line goes underneath the x squared. You know, you've just got a number in front of x squared, which is 108 over 7. So I need to multiply this by 2. I'm going to get 216 over 7 x. Okay, that's what we get when we differentiate this term here. And then I've got to set this equal to 0 in order to find the stationary points. Okay, well, there's many ways to proceed from here. I suspect some of you would take that whole fraction over the other side. Some of you would multiply through by 7 straight away. It doesn't really matter what you do. I'm now going to times through by the 7. Okay, 1296 times 7 is 9072. And then we're going to divide 9072 by 216. And we get a nice round number, thank goodness for that, of 42. Okay, and you'll notice we've only got one answer. So the question's saying find the maximum. If we've only got one answer for where the stationary points are, it has to be that maximum. If there were two answers, one might be a maximum, one might be a minimum, and we'd need to go a bit further. But we've only got one answer here, so that pretty much has to be the maximum, but I'm actually going to prove that it's definitely the maximum, okay, by finding the second derivative. So up here is my first derivative. I'm going to differentiate the first derivative a second time. 1296 will disappear, and then this term will just become the constant part of it. So the second derivative is always negative. It doesn't matter what x is, the second derivative is always negative, which means kind of the gradient is always getting less and less and less. And you've already got in your notes, as we said before, that if that is less than 0, you have a maximum. Okay. Now then, there's one little thing that we haven't done to finish the question off. If we make sure we read it, it says, hence find the maximum area enclosed in this way. This isn't an area, this is an x value. Alright, so we haven't found what the maximum area is. We've just found the x value that gives the maximum area. So you often have to do this right at the end. You have to substitute this back into your area formula to work out what the maximum area actually is. So when x is 42, a equals 1296 times by 42 minus 108 times 42 squared over 7. Oh yes, the calculator again. It's burning my fingers. Wow. That's a rather big number. Okay, but there we go. I mean, don't forget there's 100 millimeters squared and a centimeter squared, so it's probably not as big as you think it is. Okay, but there's common themes in both of these questions. There's writing down a formula for two variables, and then there's writing out a link between two variables, which is given in the question in the form of some sort of number. In the first question it was 1512 being the total length of the wire. Sorry, in the second question. And in the first question it was the sum of the two numbers is 30. Those two bits of information enable you to write links between the numbers that help you make your formula in terms of one variable. And that happened in both of the questions. Okay.